Yeah, thank you very much for the introduction. And I will try to provide an overview of different applications we've worked on in the last couple of years. So mostly I'm working on molecular dynamics problems. We are interested in detecting fast and slow dynamics and in particular dominant spatial temporal patterns. The same methods can also be applied to fluid dynamics problems where we are also interested in, for example, coherent sets. So I will show how transfer operators can be used to detect certain patterns in dynamical systems, in particular also in high-dimensional dynamical systems. And then later I want to use this analogy to develop spectral clustering methods for directed and also time-evolving graphs. So what you can show is that the Koopman operator is basically closely related also to the graph Laplacian. And then we can use this forward-backward operator that is used to detect, for example, coherent sets, to define this also on directed graphs, to detect clusters in directed graphs and also in time-evolving graphs. So it's the same method, basically. The only difference is that we don't have a stochastic differential equation that is defined on a continuous state space, but we have a discrete state space, and everything is finite dimensional, so everything is much easier. But this is what I wanted to show today. So I will start with an overview of different methods. So typically we are interested in computing metastable sets, and I will just show a couple of examples. So if you, for example, simulate a molecule, this is a simulation of a butane molecule, you can see these fast oscillations and you can see slow conformational changes. We are only interested in these slow conformational changes because this influences the behavior of these proteins, for example. This is very simple, this is not a protein yet. So we are only interested in the slow dynamics, and we are interested in how likely it is to, for example, switch from one conformation to another one. And of course, this is only a toy problem, but this is already 42-dimensional because we have 14 atoms here, and each atom has a 3-dimensional position in space, and we want to identify transition probabilities and also these stable conformations. But later we want to apply this to more realistic protein folding examples, and we want to identify again folded and unfolded states. And these are really high-dimensional problems, and here there's no underlying PDE that has a low-dimensional structure. So these are really high-dimensional systems. And we also want to apply this to, for example, different data sets. So here we have, for example, a motorcycle in a wind tunnel, and again we want to identify dominant spatial temporal patterns, which allow us to project this onto a lower-dimensional space. You could also apply this to video data. So all of these methods are really purely data-driven and can be applied and have been applied to all kinds of different data sets, for example, stock market data or traffic data or EEG data. So there are so many different applications. That's, I think, really one of the main advantages of this Koopman framework. So I don't think I have to introduce the Koopman operator, but I will also talk a little bit about the adjoint operator, which is the Perron-Frobenius operator shown here. And we are working mostly with this stochastic Koopman operator because we are working with the stochastic dynamical systems. And another operator that plays an important role is the so-called re-rated Perron-Frobenius operator. If you want to estimate the operator from one trajectory, then it's typically easier to estimate the re-rated transfer operator with respect to the invariant density typically instead of this Perron-Frobenius operator. But these are both adjoints of the Koopman operator with respect to different inner products. And later we also need compositions of these operators in order to detect coherent sets instead of metastable sets. We also consider compositions of the Koopman operator and the transfer operator. This is related to the forward-backward dynamics. And then we can use this to also detect these coherent sets, which you can view as metastable, time-evolving metastable sets. So I showed already these metastable sets on the previous slide. If these move in space, for example, then you can call these coherent sets, and they are also related to dynamics which are invariant under the forward-backward operator, for example. So that's why we are interested also in compositions of these operators. And also Alex mentioned already the generators of these operators. These are, for example, the Kolmogorov backward equation or the Fokker-Planck equation. So for a stochastic differential equation of this form here with this drift term B and the diffusion term sigma here, you can show that using E2's lemma that the generators are of this form. And sometimes instead of approximating the operator, we can also approximate these generators from data depending on what kind of data we have. But they have similar spectral properties. So once we have the generator, we can also approximate these operators and typically also vice versa. I just wanted to show this here briefly because the generator is also closely related to system identification. If you have the Koopman generator, if you apply this to the full set observable or to observables of this form here, f of x is equal to xi, so we're observing the ith component of the state, then you can see that if you apply the Koopman generator to this observable here, then you get bi, and this is how you can also define, for example, Cindy as a projection, the sparse identification of nonlinear dynamics, as a projection or the application of the Koopman generator to the full set observable. And you can use the same trick also to identify the diffusion term by applying the Koopman generator to observables of this form here, xi multiplied by xj. Then you can see that you can extract not only the drift term, but also the diffusion term. So in this sense, it's also closely related to system identification. So this is a different application. So for example, this is the Cindy approach here, you have, for example, trajectory data, and you want to identify the underlying governing equations, then you can also use the Koopman generator to identify the drift term and the diffusion term. You can apply this to SDEs, to PDEs. There are lots of different extensions. And of course, you can also apply this to discrete dynamical systems. So this is just an overview of different applications. And this is an overview of different methods that have been developed in the last couple of years. And a lot of methods have been developed independently by the dynamical systems community, for example, DMD, EDMD, and also the kernel-based versions. And independently, some of these methods have also been developed by the molecular dynamics community. There it's typically called TICA for time-lag independent component analysis. Then there are also nonlinear variants and kernel-based variants. And then in climate science, I think it's called linear inverse modeling. So the same methods have been developed independently 3 times already, and they are all very closely related. These methods work quite well for time homogeneous systems, but later I want to show that we can also extend this to time inhomogeneous systems, where, for example, the systems are time dependent or non-reversible. Then it makes more sense to talk about coherent sets instead of metastable sets. And then this generator approximation can be used also to identify the governing equations, and there are again kernel-based variants and lots of different approximations. And also, I should mention here that we don't necessarily have to use kernels. This is just one convenient way to detect these or to approximate these Koopman operators and generators. But you could also use, for example, tensor decompositions or neural networks or lots of other approaches. You can also use time delay embeddings or explicitly defined sets of basis functions. There are lots of different ways to estimate these operators. We are mostly working with these reproducing kernel Heriot spaces, which Alex also briefly mentioned already. So typically, we don't define an explicit set of basis functions, but we are using a kernel. For example, we are typically using the Gaussian kernel, which works quite well also in high-dimensional problems. So the advantage is that we don't select the basis functions explicitly. We just define a kernel. The kernel implicitly spans a feature space. And if we are using, for example, the Gaussian kernel, then this feature space is infinite dimensional. If we are using a polynomial kernel, then the feature space is finite dimensional. But there are some other advantages as well. And this typically is quite stable. The disadvantage of these kernel-based methods is that the dimension of the eigenvalue problem that you have to solve depends on the number of data points. So if you have long trajectories, then this can become very expensive. But the advantage is it works quite well in higher dimensions because otherwise you typically run into this curse of dimensionality that we already discussed in the morning. So this is just quickly to show that we can approximate these different transfer operators using kernel-based methods. What you have to do is you have to approximate covariance and cross-covariance matrices, and you can estimate this again from data, and then you get gray matrices, and then you just have to solve these corresponding eigenvalue problems shown here. And then you can compute eigenvalues and eigenfunctions or approximations of eigenvalues and eigenfunctions of the Koopman operator or also of the Perron-Frobenius operator. And there are some other operators which are closely related to also conditional mean embeddings of probability distributions, and these are, we call here, embedded operators. But the main message here is that we just have to solve auxiliary eigenvalue problems. We don't, using these kernel-based methods. So it's basically straightforward. You just compute gray matrices, you compute eigenvalues and eigenvectors, and then you get these eigenfunctions of the transfer operator. This would be a simple dynamical system just to illustrate the idea behind these metastable sets. So here we have these oscillations here, or this energy landscape. We have fast oscillations again due to, for example, Brownian motion. And then we have slow changes which correspond here to moving from one well to this well or to this well. So this would be the slow process. So in this case, there are 4 metastable sets. And what you can then see is that the Koopman operator has 4 dominant eigenvalues, then a spectral gap. And the 4 dominant eigenvalues and eigenfunctions contain information about the metastable sets. The first eigenfunction here, this is the so-called invariant density, shows you, for example, how likely it is to find a particle in one of these wells. So yellow means the probability is high, and this green part here means the probability is low. And then the next eigenfunctions tell you how you can subdivide the state space, for example, horizontally, vertically, or diagonally into different sets. So if you combine the information contained in these eigenfunctions here, you get 4 metastable sets corresponding to these 4 wells here. That's the general idea, and that's how we typically use this to identify conformations of molecules. So this would be a small example, but we want to apply this to real protein folding data. And I can quickly also show you the simulation. So this is the simulation of the protein itself. And on the right, you can see a simplified ribbon representation. And here we're interested in the folding properties. So the folding is really the slow, corresponds to the slow dynamics here. And we are interested in how the protein folds and unfolds, and again, how likely it is. So given only the positions of the atoms here, we want to identify the dominant eigenfunctions of the Koopman operator. And then we detect, for example, these folded states shown here, or some unfolded or misfolded states shown here, and you can also see how likely it is to find these conformations in these data sets. So this is an application that we are typically working on. This can also be extended to detect coherent sets. So we use kernel-based methods for metastable sets, but if these metastable sets are moving in time, then we can't use the Koopman operator in general, because the problem is that these eigenvalues are then complex valued, and you cannot sort them anymore. So you can't really detect these inherent timescales. And then the trick that Gary Frohlan proposed is to use a composition of a forward operator and a backward operator. So the trick is you just propagate probability densities, you pull them back, and then you find functions which are invariant under the forward-backward dynamics, and these are called coherent sets. And they play also an important role in fluid dynamics, where we want to identify sets of particles which move in a similar way. I will also show an example in a second. And then there are lots of applications in fluid dynamics. For example, you want to find gyres in the ocean, which are, for example, shown here. These are called Agulhas rings. They are forming here and moving in this direction. So these are areas of the same temperature, for example, or salinity, and we want to identify them, for example, from GPS tracking data or from some flow fields. You can also find similar patterns here in the wake of planes and also here in space, for example. These are just some examples. And then what you can show is that basically computing coherent sets means applying kernel CCA. CCA is this canonical correlation analysis. And if you apply canonical correlation analysis to time series data, you can identify these coherent sets. We can also show that this canonical correlation analysis basically also computes transfer operators or composition of transfer operators. So I will not go into this in detail, but the eigenvalue problem that you have to solve is shown here. And you can see that the first part is basically a Koopman operator, using again covariance and cross-covariance operators. The second part here, this is the reweighted Perron-Frobenius operator. So you get here a composition of Koopman and Perron-Frobenius. And then this is the forward-backward operator. And we again try to identify dominant eigenvalues and the corresponding eigenfunctions of these operators from data. So here we again have, for example, GPS tracking data, and we want to identify the dominant eigenvalues and eigenfunctions to identify these coherent sets. A typical example that is often used as a benchmark problem is the so-called Bigley jet shown here. And these are the dominant eigenfunctions. I can also quickly show you a simulation. So you can see here, these blue dots are all particles. So I'll quickly go back here. So I color two sets here. One is marked in yellow and one is marked here in red. And you can see that the behavior of the red set and the yellow set is completely different. This yellow set is dispersed immediately, and you don't really know where the particles started or where they will end up. Whereas this red set here is coherent. That means particles that started in this red set will remain with a high probability in this set. You can see that some particles basically escaped, but most of them remain coherent in time. So these are called finite time coherent sets. And we can again identify them using transfer operators. In this case, we are using this forward-backward operator to ensure that the spectrum is again real valued, and then we can sort them again according to the time scales, and then we can find these slowly evolving time scales. So the eigenfunctions tell you again, for example, here, this eigenfunction tells you that particles that start in the top part here will not very likely move to the bottom part. Then you have this jet here in the middle, and you have these small gyres here, which I just showed in the video. So this is another application of transfer operators and how they can be used to analyze complicated dynamical systems. And then we also applied this to real ocean data, and then we identified the main gyres. This is just an example to show how we can use this also in climate science application, for example. So here, if we use the same approach and again compute the dominant eigenvalues and eigenfunctions and then cluster them, you get a clustering of the state space into these sets here. And these sets that we identified correspond to the different well-known gyres. So for example, this red set here is the South Pacific gyre, North Pacific gyre, and so on. The only coherent set that we did not find was the splitting between South Atlantic and Indian Ocean here. But when you look at the data, you can see that lots of particles are actually moving from this gyre here to this gyre. So this set is not as coherent as the other sets. So this is just an application. But I will talk a little bit more about some new results. So you can also apply the same methods to compute eigenfunctions of differential operators. So instead of computing the Koopman operator, we can also compute, for example, the Koopman generator, which is a differential operator. Or we can also use this, for example, for the Schrödinger equation. I will just quickly show one or two examples. And then I will talk a little bit more about spectral clustering and how we can use the Koopman operator to identify clusters in networks. So here the idea is that we are again using kernel-based methods, but here we have to use not this reproducing property, but you can show also that you can reproduce derivatives. So you can use this in the very same way again to identify these operators from data, and then we can again compute dominant eigenfunctions. So I'll just show two examples. We applied this to, for example, the quantum harmonic oscillator, and we identified these eigenfunctions which are well known. So this is a very simple quantum mechanics problem where you can really compute the eigenvalues and eigenfunctions analytically. So we just used this as a test problem to check whether we really get the same solutions. And you can see here, again, we have to solve some eigenvalue problem. The only difference now is that we are not approximating the Koopman generator, but we are now solving the Schrödinger equation here. The operators look slightly different. They are now related to the Schrödinger equation. So you can see here the Laplace operator, and this would be the potential of the quantum mechanics problem. But then in the same way, we can compute, again, eigenvalues and eigenfunctions. So it's just a slightly different operator, but the same idea in principle. And there are two different ways to do this. So the first way would be to directly discretize the Schrödinger equation and to compute these eigenfunctions. Another possibility is to transform the Schrödinger equation into a backward Kolmogorov equation, which is then again the generator of a stochastic differential equation. So we can also use standard EDMD and these techniques that I showed at the beginning for these molecular dynamics problems to also identify eigenfunctions of the Schrödinger equation. So there are two different ways to do this. And this is also closely related to Nelson's stochastic mechanics, which is a probabilistic formulation of quantum mechanics. So you can show that these operators and these techniques are closely related. So the idea is to transform the Schrödinger equation into a stochastic differential equation and then to compute, again, eigenfunctions. And here we did this, for example, for the hydrogen atom, and then you identify the ground states and some of these excited states, for example. So it works in a very similar way. So the last application I briefly wanted to talk about is spectral clustering of graphs. It's not switching to the, oh no. Okay, so we've already seen the difference between metastable sets and coherent sets. So coherent sets are just time-evolving metastable sets, and we want to identify them again from data. And now I want to define these transfer operators also on graphs, and then I want to compute dominant eigenfunctions or eigenvectors in this case again to identify clusters in a graph. So if you have a graph of this form, for example, V is given by the vertices V and the edges E here, as shown here, then the standard spectral clustering approach is as follows. So you just define this out degree matrix here, and then you can define the so-called random walk normalized graph Laplacian, which is simply the identity matrix minus the inverse of this degree matrix multiplied by this adjacency matrix here. And this matrix, which I called S here, is a stochastic matrix. So this is basically used to generate random walks. So the entry Sij contains the probability of going from vertex Vi to vertex Vj. And then we use this here as a very simple benchmark problem. These dashed edges here have lower probabilities or lower weights. And then basically you have here three, again, metastable or coherent sets. If a random walker starts in this cluster, for example, it will stay for a very long time in this cluster before it moves to this cluster. So in this sense, this is very similar to the molecular dynamics problems that I showed at the beginning. And these are two different random walks. You can see here, the random walkers will spend a long time in the first cluster, then it moves to the second one, and so on. The problem here is that spectral clustering methods don't work necessarily for directed graphs because, again, the graph Laplacian has complex eigenvalues. We can't sort them according, for example, to time scales. And the eigenvectors are also complex valued. A standard approach or a very simple approach would be to just consider the real parts, but that also doesn't in general work. You typically won't identify these clusters here if you just symmetrize the problem or neglect the directionality of these edges. So the idea here was to, again, use this trick that is used for computing coherent sets, and then we can also define coherent sets to be clusters in, for example, directed graphs or time-evolving graphs. So because you can see here, the behavior is very similar. The only problem is now that this process is not reversible, but we can fix this easily by considering compositions of the forward and the backward operator. So this would be the standard spectral clustering approach. You just compute the dominant eigenvectors of the random walk normalized Laplacian. And you can view this basically, this matrix S is basically just the Koopman operator. And then you can compute also the Frobenius operator and the other operators in the same way. And then you, in this case, we would identify 4 clusters. But we want to extend this now to directed graphs and also time-evolving graphs. For example, if you have a social network, then you might add edges, or edges are removed again if you unfriend someone. And that's why we are also interested in time-evolving graphs. So we just use exactly the same operators. So these are the operators that I defined at the beginning. Frobenius, Koopman, this reweighted transfer operator. And this is now a composition of the forward and backward operator. And this is a composition of the backward and forward operator. And we just define exactly the same operators now on these graphs. And you can see that the only difference is that we have to replace these integrals by sums. And then we have again the same transition probabilities here. And the transition probabilities are based on the weights of these edges of the graph. And yeah, in this sense, we have exactly the same operators. The only difference now is these are infinite dimensional linear operators. These are just matrices because the state space is finite dimensional and everything is much easier. But otherwise, it's the same idea. And then you can also show that computing these eigenfunctions of the forward-backward operator is equivalent to computing singular functions. So it's basically, again, a spectral decomposition of the Koopman operator. We're just computing left and right singular functions instead of eigenfunctions, but everything else is exactly the same. I'll just show a couple of examples and the properties here. So I mentioned already that these transfer operators in this case are just finite dimensional objects, so we can represent them as matrices. And you can see that the Koopman operator is basically just the stochastic transition matrix S itself. The Perron-Frobenius operator is the matrix S transpose. And then you can also compute this re-weighted operator and these forward-backward operators. And these are the operators that we are using for finding coherent sets. And we can use this now also for finding clusters. And the main property that we need here is that the eigenvalues of the forward-backward operator and this backward-forward operator here, they're again real valued. So it again makes sense to talk about timescales. And then we can apply clustering techniques to the dominant eigenvectors to identify these sets. So I'll just show a couple of examples. And you can also show that this forward-backward operator is a form of symmetrizing the system as well. So if we take again this very simple benchmark problem here, if you compute the structure or the structure of the matrix of the forward-backward operator, you can see that it's basically a symmetrization. You get a symmetric matrix with respect to some sometimes re-weighted inner product. You can see that if we apply spectral clustering approaches now to this graph, we can identify again clusters using conventional spectral clustering methods. And this would be the structure of the backward-forward operator. So we are just adding a couple of edges. For example, you can here go from 4 to 8 because there's a walk in forward direction from 4 to 5 and in backward direction from 5 to 8. That's why there are a couple of additional edges here. And then the trick is again, we just compute the forward-backward operator. Now on this finite state space, we identify the dominant eigenvalues. So there are, in this case, 3 dominant eigenvalues. If we take a look at the corresponding eigenfunctions, you can see that they have different level sets corresponding to the different clusters. If we cluster then these graphs, then we get these clusters. So this works quite well for directed graphs. And this is, I can also quickly show this here. This is basically now a visualization of, takes a little bit, a visualization of these random walk processes. So you can see again, we have these random walkers here, and these sets here that we identified are coherent because if a random walker started in one of these sets, it's not moving anymore, but then they will remain in these sets for a very long time. So in this sense, they are coherent sets. That's how you can view this. It's just a slightly different interpretation. Okay, so we can use this for directed graphs, and we applied this also to some benchmark problems. But I will quickly show how we can apply this also to time-evolving graphs as the last example. And this is shown here. So here we have, for example, a time-evolving graph, and we want to identify, again, different coherent sets. So this is now a time-inhomogeneous problem, and the system is designed in such a way it's just rotating. So the coherent sets are rotating with the graph. And you can see, again, in this case, there are only 2 coherent sets. You can see, for example, this green set here, this is a coherent set. This red set would also be a coherent set. And then you can see that if we compute the dominant eigenvalues, there are 2 dominant eigenvalues corresponding to these 2 coherent sets. And this yellow region here is the transition region. So the random walkers will either move to the red part or to the green part. So you can see that the eigenvalues and the eigenvectors really contain important information about the structure of the graph. One last example that I quickly wanted to show is this graph that we constructed. The graph is based on this quadruple gyre problem that is also often used to detect coherent sets as a benchmark problem. So you can see that this is now a time-evolving graph. So the graph changes in time. Some edges are added or removed again. And here, I want to identify clusters by computing these coherent sets. And if we apply these methods to compute the coherent sets based on the eigenfunctions of the Perron-Frobenius of the forward-backward operator, then these are exactly the sets that we identify. So these are the 4 gyres of this quadruple gyre problem. Just very briefly, we want to apply this, of course, to more realistic networks. So this would be, for example, a social network. This is called the high school contact and friendship network. It's based on an experiment. I think this was conducted in France, where students were wearing a sensor whenever 2 students were facing each other, and a link was established. And then this was done throughout the entire week. And you can see here the adjacency matrices for different days: Monday, Tuesday, Wednesday, Thursday, and Friday. And then the question is, can we identify clusters, basically groups of students who behave in a similar way or attend, for example, the same classes or talk to each other more often than to other people? And what we see here is that the clusters that we identify correspond to exactly the classes that the students take. For example, this cluster is, for example, some biology class. This might be a mathematics and physics class, and so on. So in this way, we can also use the clustering techniques to identify groups of, for example, students or groups of people in a social network which share similar interests or behave in a similar way. Okay, I think this was a rough overview of the different topics. So I just mentioned applications in molecular dynamics and fluid dynamics and in climate science and also in quantum mechanics. Of course, there are also lots of other applications, computing, for example, attractors. This goes back to Michael Delnitz and Oliver Junge and Gary Freundland as well. It can also be used for system identification. We've already talked a little bit about on control. And also, I just briefly mentioned that we can also use this for detecting clusters in, for example, networks. So there are lots of different applications. And the idea is that we always use time series data or simulation data to identify these dominant patterns of dynamical systems. For example, metastable sets, coherent sets, or ground states of a quantum mechanics system. So these are all different applications of Koopman operator theory. And you can see that these systems can be quite high-dimensional. And this is, I think, the main challenge at the moment to apply this to high-dimensional problems. And yeah, with that, I will just stop here. Thank you very much.